Alright, I've made a couple of attempts to create these videos without much luck, so I hope this one is going to record this time. If you go on Northview's website, log into Edline, go into your course, the link to your course for your math class, underneath on the right hand side, underneath the weekly reviews, you'll find some examples that I typed up, and I have cut and pasted those examples into this software that I have that allows me to kind of explain my solution in a video form. So I won't go through all of these examples on this video. I'll have to break it up into multiple videos. But on the very first thing here is these 18 examples. Now you may not need to review or refresh yourself on all of these types of factoring problems. So you may have to jump to other videos to find the example that you want to look at. Alright, so let's begin. Very first example asks us to factor x squared minus 9. I see two terms here. Terms are separated by addition or subtraction. And I also notice that each term is a perfect square. That here, this base x is being squared. And I can rewrite the number 9 with a base of 3, and 3 squared is 9. So many of us have it memorized, a formula that allows us to factor the difference of squares. Now you'll also notice that I should have started out by saying, hey, the first step in all of these, and I did have it pasted at the bottom below all these examples, whenever you're trying to factor anything, the first thing you want to look at and stuff is, do the terms have a greatest common factor? You want to factor out that greatest common factor. Well, x squared and 9 are relatively prime with each other. They don't share a common factor. So I was able to jump in and say, okay, I see this as a difference of perfect squares, and I have a formula that I've memorized. The a squared minus b squared is equal to the product a plus b times a minus b. So now, just as a substitution, let a be the base x, let b be that base of 3, and you have x plus 3 times x minus 3. Now I also have another solution to the same problem, because maybe for some reason someone doesn't have this memorized or is unsure of the formula, or they just didn't take the time, they didn't recognize that it was a difference of perfect squares. The algebra team here at Northview, when you were taking Algebra 1 and Algebra 2, has taught us a method that they refer to as an X method to factor trinomials. Well, this is a binomial. This is two terms, and you think to yourself, a trinomial always has three terms, and we focus in initially on the middle term. Well, we can rewrite this expression. We look and we see that there's no greatest common factor. That's that first step. And we didn't notice maybe that 9 was a perfect square. This X method, we rewrite this x squared minus 9 as x squared plus 0x minus 9, because 0 times anything is 0. We can add that 0 term, and it's not affecting this algebraic expression. This expression is still equivalent to x squared plus 0x minus 9 is equivalent to x squared minus 9. So you place an x over the middle term. The top of the x you always get by multiplying the first term times the last term. I have a sign error there, don't I? The x squared times negative 9 is a negative 9x squared. Two numbers that when multiplied together give us this negative 9x squared, but yet when added give us this 0x. Well, we come up with negative 3x and positive 3x. You multiply them together, you get the top of the x. You add those together, you get the bottom of the x. So when your leading coefficient is 1, then we don't have to, we'll see in later problems that when that leading coefficient is different than 1, that we'll make a table, and we'll come in and use our table to get our final expression, to get our final factors. But here, with the leading coefficient of 1, we can use the negative 3 and positive 3, and we can say that the x squared plus 0x minus 9 is equal to this product of x minus 3 times x plus 3. All right, so let's go on to the next example. So the next example here is a trinomial. I do not see any I have three terms here, and I do not have a greatest common factor. There's no common factor to all three terms. Remember, that's always going to be that first step each time we're trying to factor. I also notice that this expression is written in a form that I need, that I want, that I'm very comfortable with, and that's that the exponents on the variables are written in descending order. Remember that x to the 0 is by definition equal to 1, so I can even put an x to the 0 here, and I can see my exponents 2, 1, 0 are in descending order. Now, we typically don't put this x to the 0 there, but that's just to point out that it is in descending order. All right, so we use this x method that we learned previously in our other courses. We place an x over the middle term. To the top of the x, we take the first term times the last term, 2x squared. Now that the hunt begins to find two values that when multiplied together give us the top of the x, but yet when added together give us the bottom. So since this is a positive value, this 2x squared, and this is negative, the negative 3x, we know that what we're looking for is two negative values. The negative times the negative is positive. When we add these together, we get the negative 3x. See, the arithmetic involved here, the multiplication, is pretty simple because of this 2 of x being a prime number. There's not a lot of different combinations that we have to go through. When we have a leading coefficient that's larger than 1, and especially when it's not a prime number, and the top of this x, when it's a very, very large number, why, it takes a little bit more trial and error to find these two values, and I show that in some later examples that we'll look at. But now with the negative 2x and negative 1x, we can jump right in and say that, hey, this factors to x minus 2 times x minus 1, and if you have time, it's always a smart thing to check your answers, and a nice organized way to multiply binomials is to use a table. And now the x times x is x squared. The x times, see, here's part of the values that we found in that x, the negative 2x, and then here negative 1x, and a negative times negative is positive. So if we add these four terms together, it simplifies to x squared minus 3x plus 2, so we know we've done it correctly. All right, so here we have another example. It's similar to the last one, but there is some minor differences. The middle term here was negative, so I knew that, and here a positive. I knew that I was looking for two negative values here. Negative times negative is positive, but when it's added, it was negative. Well, now with the last term and the middle term both being positive, I know that in my x, all those are going expressions are going to be all those coefficients are going to be positive. So, you know, we look at this and we see that there's no greatest common factor among these three terms. It's in the proper form. It's in descending order. We use this x method. We can draw an x right up above that middle term. Take the first term and the last term to get the top of the x. Now the search begins for looking for two numbers that when multiplied together give us this 3x squared, but when added give us 4x. Because 3 is a prime number, it's relatively easy to find that 1x times 3x is 3x squared, and 1x plus 3x is 4x. Since this leading coefficient was 1, we can just come in and say I can factor this to x plus 1 times the quantity x plus 3. And again, if you wanted to check that, you could create a table and multiply it. And of course, if you're familiar, a lot of people can just do that in their head. They don't have to necessarily write that out. All right, so now we have a problem here that's different in a couple of ways. 2x to the fourth minus 6x squared. I have three terms. I notice that all of these are even numbers, so I am going to have a common factor to all of these terms, the number 2. But I also notice that this is x to the fourth. It's not a quadratic. It's not x squared. Well, when we're trying to factor that, like I say, we look and we see that we have the greatest common factor of 2, and I can factor that 2 out, And when I do that, I get x to the fourth minus 3x squared minus 4. So there's my new focus. This trinomial right here is what I'm going to try to factor. And I notice two things. I notice it's a trinomial. I also notice it's in the correct form in descending order. But the degree of the middle term, 2, that's half of the degree of the first term. This first term, the exponent is 4. This term has a degree of 4. This middle term, it has a degree that's half of that. Anytime that's half of that, that's when we can apply that x method that's going to work. So from our algebra course, we know how to apply the x method. We draw an x above the middle term, take the first term times the last term for the top of the x, and then the trial and error begins. We look for two numbers. When multiplied together, give us the top value, but yet when added, give us the bottom value. With both of these being negative, one's going to be positive, one's going to be negative, and the larger in magnitude is going to be the negative number. 1x squared times negative 4x squared gets you the negative 4x to the fourth, and yet when you add those together, you get the minus 3x squared. So if we come down, I guess we necessarily didn't have to create the table here. I put the table in there initially because I saw a leading coefficient that was different than 1. But I know that the 1x squared and negative 4x squared are going to be in my factors. But we can, I'm illustrating that if you do along one diagonal, write the first term and the last term, and along the other diagonal, write the values that you found in your x, you've now created a table to where, remember when we did the table to check our answer before, we already knew the values on the outside and we multiplied to get the values on the inside. Well, now you're working in the reverse order. You're working on the inside of the table, inside outward, and you do that by factoring along each row and along each column. So we see that there's x squared and minus 4 are relatively prime to each other. They don't have anything in common, so we just have the value 1. We look in this column and we see that the negative 4x squared and negative 4 have a negative 4 in common. And then also we look and see that the x to the fourth and negative 4x squared only have an x squared in common. So it's easy to get the outside of this table and to check it. X squared times x squared is x to the fourth. X squared times negative 4x squared. 1 times x squared, 1 times negative 4, negative 4. So once you have the outside of this, you're able to write your factored form. Remember, it had a 2. We don't lose that common factor of 2. Now have the x squared plus 1 and x squared minus 4. Well, you might be tempted to stop right there and you get an incorrect answer because it asks us to factor it, but it also wants us to factor it completely. This x squared minus 4 is a difference of perfect squares. The base x is being squared, this base of 2 is being squared. So if we're familiar with our formula, that a squared minus b squared is a plus b times a minus b, we can recognize that this x squared minus 4 factors to x plus 2 times x minus 2. If you don't recognize that formula, again, you can do the x method on that. But I'm going to assume that we can remember that formula and stuff, especially that we've pointed it out in a previous problem. So if this x squared minus 4 factors to the x plus 2x minus 2, I'm ready to write my final answer because I had that common factor of 2. It factored to the x squared plus 1, x squared minus 4, x squared minus 4 factored. Now, one observation, if you have a difference of squares, it factors, but if you have a sum of perfect squares, it does not factor over the set of real numbers. Now, if we were using complex numbers, we could factor it, but we're using the set of real numbers, so we stop right there and we say that we have factored this completely. But when you have a sum of squares, we cannot factor that within the set of real numbers. So you had to stop with x squared plus 1, but you were able to continue with x squared minus 4. All right, so here we're back to an example that's easier than the last one. We have a trinomial, leading coefficients 1, it's written in descending order, and there's no common factor to these three terms. So we can jump right in and think about two values that when multiplied together give us the negative 5x squared, and yet when added give us 4x. We do that just with scratch work by placing an x over the middle term. And then since that leading coefficient is 1, the negative 1 and 5 become our factors when we factor that to two binomials. All right, so now this one, it's the same idea. It's a trinomial, and it's a quadratic, but now we see that the values are considerably larger. We notice that that all of these numbers are even, so that at a quick glance I know it has a common factor of at least 2, but I might have to grab a calculator and look and see, yeah, if there's some value that's larger than 2 that also divides. So I don't want just the common factor, I want the greatest common factor. So 8 divides all of these terms. Yes, it was true that 2 divides all of them, but then after you factor that 2 out, you'd see that 4 also would have divided the rest of it. So we're going to factor out a common factor of 8, and that's pretty simple to do. Divide each term by 8, and we get 40 divided by 8 is 5, 208 divided by 8 is 26, and 192 divided by 8 is negative 24, or negative 192 divided by 8 is, it's pretty early in the morning here, I haven't fully woken up. So now we focus our attention on this trinomial. We set aside the common factor of 8 for a moment, but we do have to remember to include that in our final answer. And I think it's one of those things that you can now focus so much on factoring this other part of it that in your final answer you forget to write that factor of 8. So you do have to get into a habit to remember to include that in your final answer. So the 5x squared plus 26x minus 24, we use the x method. The leading coefficient is not 1, but it is prime, so this is not going to be too difficult. We're looking now for two numbers that when multiply together give us the negative 120, but add together to give us the 26. So that might take a little bit of scratch work, and you may want to come up with an organized way to search for that. Now, some people are pretty gifted in arithmetic, and they can find that by just guesswork. I often have to look at it in a little bit more organized way. Remember that what we're looking for is this 5x squared plus 26. This was the original problem, so I should probably write here, since we're focused on this 5x squared plus 26x minus 24. So the 5 times the negative 24 is negative 120, and when we add it together, we're looking for 26x. So when if I just forget about the variables for a moment and just look at the numerical values, I'm just going to start with multiplying two numbers together that will give me the negative 120. And so I know that one value is going to be positive, one's going to be negative. I know that I let the smaller number be negative, because with the last term being negative and the middle term being positive, I know the one that's larger in magnitude will be the positive number. So I know that if this is going to work out, 1 is smaller than 120, 1 would have to be the negative value, 120 would have to be the positive, because that middle term is positive. So I multiply those together, and hey, I found two numbers that multiply together to give me negative 120. But the problem is, when I add these together, that sum is not 26. So I move on to the next number, and I notice that this negative 2 divides the 120. So I have a product that's equal to negative 120, but my sum, when I add these together, is not the number I'm looking for, 26. So I just continue along. I come to the next number. I plug it in the calculator. It's not a decimal number. When I take the 120 divided by negative 3, I get 40. But yet when I add those together, 40 and negative 3, I don't get positive 26. So I move to the next one, and now all of a sudden, when I take 30 times negative 4, I get the product that I want, the negative 120, and I also get the sum that I want. 30 plus the negative 4 is equal to 26. So there we found it. This was the one that we were searching for. And some people are extremely gifted at just almost finding that immediately and stuff. They don't really have to go through the step-by-step process of trying to find that. Others, like myself, not being good enough at mental arithmetic, I have to have some organized way. So if you begin to also look, what I often do is I may not do it in quite the sequential step. I look at 120 and I write its prime factorization. I take 120 and say, well, I know that 2 times 2 times 2 times 3 times 5 is 120. I played around with the calculator to know that. Okay. So now I'm going to look for the right combination of these values. So the first time, this 60, you just take the one of these factors of 2 over here, and the 2 times 2 times 3 times 5 is 60. And 60 times 2, hey, that's that 120. I haven't worked with the negative signs, but you can see the idea that with the prime factorization, I'm looking for the correct combination. So on the next one, I've factored out a 3 from there, pulled a factor of 3 over here. The rest of the product here times the 3 gave me the 120. But of course, when I added those together, I didn't get 26. And here, this is the right shuffle, the right combination of these prime factors that I needed. 2 times 3 times 5, 2 times 2. The 2 times 3 times 5 was the 30. 2 times 2 is 4. And the difference of that gave me the 26. So sometimes if the larger this number is, in order to reduce my list, I'll look at the prime factors. And looking at this list, I'm sometimes able to quickly find the right sum, the 40 and the negative 4 that would get me the 26. All right. So now that we found the correct values, we can make a table. So within my X method, I found that 30x and negative 4x were the numbers that I was in search of. So I go back and I take the first term and the last term, and I write that along one diagonal of my table, and then the 2 values in the X that I found, I write that along the other diagonal. And I look and I say I need to look and see what common factors there are by each row and also by each column. So when I look at 30x and negative 24, I see that the factor they have in common is a 6. When I look in this vertical column, the negative 4x and negative 24, I see that the factor that they have in common is a negative 4. And 6 times negative 4 is negative 24. I look, like I say, at say this horizontal row here. X is what's common to both, so I factor out an x. And I look vertically here, and 5x is common to 5x squared and to 30x. So when I have factored this by each row and by each column, I have my answers here on the outside of the table. This binomial x plus 6 and this binomial 5x minus 4. And remember my comment, I can't lose that common factor of 8 that was my first step. I can't say that x plus 6 times 5x minus 4 is equal to that original trinomial that I had. I need that factor of 8 in there. All right. I'll stop here for the first video, and I'll continue on the second video with example 7. I want to hopefully check and see if it recorded what we just did.